In this section, we're going to be going from exponentials to logarithms and then from logarithms back to exponentials. They mean the same thing. So when you see a base with an exponent, we call that exponential, that equals an answer. We could rewrite that as a log, and we'll put the base down here in the superscript. That's the base of the log. And we'll put the answer here next to it, and it's going to equal the exponent. So a log is a fancy way to write an exponent. Okay? So let's just go through these and kind of get the idea. So for the first one, 2 is my base, and 3 is my exponent, and 8 is my answer. So I can write that as log, the base goes here in the subscript, the answer goes next to it, and it's equal to 3. The exponent is what the log is equal to. Okay? And if you think about it, it kind of makes a circle here. If you were to rewrite it as 2 to the cube root to the cube equals 8. Let's do the next one. So our base is 1.6. Our exponent is p, and our answer is q. So I can rewrite that as log. The base goes here, the answer goes here, and it's always equal to the exponent. All right, now we're going to go the other direction. Okay, so looking at this log, we know that the base is 49. Okay, and we know that the exponent is k. And that leaves this to be our answer. So we can rewrite it as 49 to the k is equal to 7. So we've rewritten all those either from exponentials to logarithms or logarithms to exponentials. They really are the same things, and you use the way that is easiest for you in the circumstance. Now the next one asks us to evaluate each. So let's just use what we just learned in our last problem. So we know the base is 6, but we don't know what the exponent is. That's the question, isn't it? We're trying to figure that out. But instead of a question mark, couldn't we just give it a letter? Let's just call it x. That means it's unknown. So 6, the exponent is x, and it equals square root of 6. So we know that square root of 6 could be written as 6 to the 1/2. So x is equal to 1/2. Okay, let's try the next one. Our base is 4, and we don't know what it's equal to, so we're going to put an x for our exponent, and it's equal to 1. So 4 raised to what will be equal to 1? Well, x would have to be equal to 0. Let's try the next one. Okay, this one they actually did assign in a variable. So we're going to say the base is c, the exponent is d, and it's equal to g. Okay? And then last, so this one we could say the base on a log is always 10. If it doesn't show one, it's 10. So if you have no base shown, it's 10. That's the most common base for base 10. So 10 raised to x is equal to -13. So is there any exponent that I can raise 10 to and get -13? No, there's not. So this is called undefined. If you remember, when we defined log in the notes, we said that x has to be greater than 0. So you must have a positive here. In the next section, it asks us to evaluate each logarithm. In this section, we're going to use a calculator. Now, I don't even need to use my calculator, but you can put it in. If you use your calculator, it's going to say error because we just said that x has to be greater than 0. So this is undefined. And the reason is because of x must be greater than 0. But let's look at this second one. Let's get the calculators out so we can practice finding logs in the calculator. So I want to press negative because we have a negative in front of the log. And then I'm going to hit the button that says log right here. Okay. Now, notice there's a parentheses. I want to make sure that my parentheses is closed. And then I'm going to hit enter. And I can see that my log is negative 0.669. Now, I want to make an important point here. Notice that this one, when I take the log of a negative, it's undefined. But I can have a negative in the front. That's okay. Okay? I just can't have a negative of what I'm taking a log of. Now, the next part wants us to find the inverse of each exponential function. Now, let's just see. We can do the inverse exactly the same way we did before. So I'm going to swap my x and my y. And then I'm going to rewrite this as a log. So log of base 0.9 of x equals y. But in place of y, I'm going to write the inverse x. So my inverse is equal to log of 0.9 times x. Okay, so you can memorize this, or you can just realize that that's what it means. That normally you would write b of x equals y, and you'd rewrite that as the log of b of y equals x. But since we're doing the inverse, the x and y are swapped. Or you can do this like I did and just rewrite it. That's what I typically do. Let's just do the next problem. So if I were to rewrite this, I'd write this as y is equal to 4.7 to the x. If I wanted to find the inverse, I'm going to swap my x and my y. And I'm going to rewrite it as a log. So log of base 4.7 of x is equal to y. And then I'm going to change out the y for the inverse of x. Now, transformations, they work the same way as the previous functions. So the exponentials, the quadratics, all those basic functions, the same thing. We said that if there's a number outside by itself, like a -4, that means we're going to go down 4. If it had been a +4, we go up 4. Then we look at the function that's the expression that's with the x. This one's a little trickier to me, but it says -2. So I always think of minus meaning to the left, but actually it means to the right, just like on those basic functions. So I'm going to go down 4, and I'm going to shift right 2. Okay, let's try the next one. Now, this one here, I could rewrite, if it confuses you, with the 7 on the right. Is the 7 a constant by itself? We know that's going to be the shift up or down. So it's going to be shift up 7. Okay, then I look at my x expression, and it says +1. So I'm going to shift left 1. And then I have one more thing to look at, this minus in the front. And just like before in the basic functions, if there's a minus in the front, we're going to reflect about the x-axis. So these work exactly the same way. If the minus is in the front, it reflects about the x-axis. If the minus had been inside of the expression with the x, then we're going to reflect about the y-axis. And in that unusual case, then your shifting left and right is actually the way you read it. So it would have been a plus would be a right and a minus would be a left. But that only happens when there's a reflection about the y-axis, just like the basic functions. The next problem asks for the domain and the vertical asymptote. So it wants to make sure that we kind of remember what these graphs look like. So a basic log function, I always remember that the log of 1 is 0. That's the easiest one to remember. So it looks sort of like this. So you can see it has a vertical asymptote at x equals 0. This is when you need to just burn into your head. That's what a basic parent function of a log looks like. Okay? So we can see that this one is going to shift right 12. So when it shifts right 12, the vertical asymptote will shift also. Instead of being x is equal to 0, it will be x is equal to 12. And it also asks for the domain. If our graph is shifted over here, and now we have a vertical asymptote at 12, then our domain will be from 12 to infinity. Remember, the vertical asymptote means it's not going to include 12. Let's try the next one. So this one here, if I were to think about it, this would have to be, this is a little different. So I can't picture this as easy because it's not just a direct shift. It has a stretch in her too. So instead, I have to say to myself, I know that a log, we said that this has to be, let's use an x instead. The log of x has to be greater than 0. That was how we defined it. So 7 minus 6x must be greater than 0. Therefore, if I were to subtract 7 and divide by -6, when I did that, I'd have to swap the direction of the sign and say that x has to be less than 7, 6. So my domain would be -infinity to 7, 6. Now my vertical asymptote will be at that boundary point where that domain ended. So my vertical asymptote will be x is equal to 7, 6. The next problem gives us an exponential, and it asks us to find its inverse. So we can do this. So instead of y is equal to 5 to the x, I'm going to swap it and write x is equal to 5 to the y, and then rewrite it as an inverse. So my inverse will be log base 5 of x is equal to the inverse. Now it asks me to complete the table of values for each function. So all I need to do here is put in my x for my in my original function and then evaluate it. So if I say f at -2, then I put it into the exponent in place of the x, and I'll get, can bring this down like this. So 1 over 25. Let's do f at -1. I rewrite it as a positive exponent. So it's going to be 1 over 5. 5 to the 0 power is always going to be 1. 5 to the first power will be 5. And 5 to the second power will be 25. Okay? Now, to find the values for the inverse, well, we already know how to do this. We're just going to swap the x's and the y. So I can just rewrite this. Here we go. That was easy. Now we're going to graph both functions by hand. So I used the points that were in my two tables, and I drew the graphs for f of x and then the inverse of x. And you notice, like in the previous chapter, we realized that inverses are always symmetrical about this y is equal to x line. So we have more transformation practice. We have to think this by now. We know that the log function, I always use log of 1 is 0. That's a great one to always kind of use as a base. And then I can sketch it out like this. That's my basic function, right? So log of x is equal to y. So use that parent function. Now, our function tells us we're going to shift right 3. I like to use that handle, that 1, 0 handle, as a good way to move things. So instead of 1, 0, it's going to shift 3 to the right. So it's going to be 4, 0. That's one point that I have on my graph. I can also use the random point that I pick. So let me just say, when x is equal to 6, well, then that would be y is equal to the log of 6 minus 3, or log of 3. You could enter that coordinate too. You could say 6, 0.477. Give yourself a second point. Now it says also, let's see, we said the transformation would be, I'm going to shift right 3. And it says state the vertical asymptote. My vertical asymptote on my parent function, my basic function, will be x is equal to 0. And since I shifted right 3, my new vertical asymptote will be x is equal to 3. So let me just kind of tweak my graph a little better here. So I'll have a vertical asymptote at 3. And this should go a little more like that. Let's look at our next problem. This one we can see it shifts down 3 and left 4. So I always visualize what it looks like with my parent function. My parent function, I know it always goes through 1, 0. Those are my go-bys for my parent function. And I know it has an asymptote at x is equal to 0. So this is my parent function. And since it shifts down 3 and left 4, my vertical asymptote will shift left 4 too. So instead of being x is equal to 0, it'll be x is equal to -4. Like I said before, I always like to think of this as like a handle, and I pick it up. So it's at 1, 0 for the basic function, but since I shifted it down 3 and then left 4, the new point is going to be at -3, -3. Shifted it left 4 and down 3, okay? And if I want to find out where it crosses that vertical axis, then I can always find out the vertical intercept by saying x is equal to 0. So y is equal to the log of 0 plus 4 minus 3. Graph that as my first point, and I'm just going to pick another point. Let's just pick x is equal to 5, just to see what we get. So this will be log of 5 plus 4 is 9, and then minus 3. Now, when you're in this calculator, make sure you close that parenthesis so this stays as just the log of 9. Sketch it in now, like this. And I labeled those points. I labeled this one, I labeled this one. I actually gave it the vertical intercept also, so we gave it a little extra point. But the more points you have in, the better graph you can have. Now, this is a word problem, so I'm going to ask you to pause the video and read it, because the most important thing is to start by understanding what the word problem is saying. So the problem is describing an earthquake, and it had a magnitude 8.8. This is called the Richter scale, and each earthquake is assigned a number based on its wave energy. Now, they ask us to find the intensity of the earthquake in terms of a standard earthquake. So I wanted to go over this equation with you. So I, with a little nod, a little 0 here, we typically think of that as initial, but in this case it's used differently. So I nod is a standard earthquake. It's used as a reference, okay? So we're basically going to compare the earthquakes. I is the earthquake we're given. So I filled in the information we're given. We know that it was a Richter scale of 8.8, sorry. And I entered in the equation too that we're given. This is a formula that you would be given. I wouldn't expect you to memorize it. But it's just basically showing that when you compare earthquakes, it's logarithmic. So if I wanted to figure this out, if I wanted to find out what I was, then I could rewrite this as an exponential. So this would be, what is our base? So in case I haven't emphasized it enough, if you don't see a base, if there's no base given, we're going to assume it's a 10. That's the most common base. So for this one here, our base will be 10. My exponent is 8.8, and that will be equal to I divided by I sub 0. Okay? That I nod. Now, I want to solve for I, so I'm going to say 10 times the power of 8.8 times I naught is equal to I. So this tells us that our earthquake in Chile was 630 million, more than that, times what a standard earthquake is.